In this problem, we're told that a device is attached to the outside of a pressurized tank as shown. The attached wall of the device has a square cross-section. Find the resultant force on the wall attached to the tank and the vertical location at which it occurs. Specific gravity of oil is 0.9. All right. We are going to solve this problem using the pressure prism method, which states that the volume of the pressure prism, so-called volume, is equivalent to the resultant force acting from a fluid on a submerged rectangular, typically surface. Okay. Now, I am going to draw a side view of the pressure distribution for two cases. So, case one is going to be unpressurized tank. So in an unpressurized tank, starting at the surface of the fluid, supposing this is our surface, so this would be a side view of our surface. The pressure at the top, gauge pressure, will be 0. And at the bottom, it'll be, gamma times h, whatever, this total height. But for a pressurized tank, we do not have the same pressure distribution. The shape would look something like this. Here is our section. Now we're asked to solve for the resultant force, so that's the volume of the section acting on the surface. So that doesn't include this top volume. Does not include the top volume. But it's important to note that this volume is not the same as this volume, because this volume is larger than this volume due to the pressure at the surface, the 50 kPa acting by the air onto the fluid. All right, so I am going to erase the unpressurized tank case, since we know that's not what we're interested in. And we're going to take a look at this one. Okay. So we want the volume of the pressure prism acting on the surface. If we take a look at the cross-section of this volume, we have two components. We have a square component and a triangular component. So I labeled them component 1 and 2. And I'm going to keep everything in terms of variables here. So let's see, from here to here, we'll call this one H1. We'll call this one to the bottom of our surface H2. All right. So the way this works is the widths of the pressure volume are pressure. So at the top, our pressure is not a rectangle, pressure of the surface, in our case 50 kPa. Now for section 2, our pressure is going to be the surface pressure plus gamma times H1. So that is the addition of the air pressure plus the fluid pressure. The fluid pressure is defined by gamma times the height. All right. We can determine this length quite easily. We know these lengths, so H1 in this case would be 2, H2 would be 2 plus 0.6, and just looking directly, this is 0.6. So that's known. So, and we also know that our section here of our surface is square, so we know the depth. So we can calculate the volume of 2 as things stand right now. Now, how do we calculate this volume? Because we have to add this volume to this volume. Well, we need this width. So let's take a look at what this volume would be, or this length rather. So this length at the bottom of our pressure prism, simply the surface pressure plus gamma times H2. Now, we can determine this width in order to calculate the volume of section 1. This is simply equal to the bottom largest most length. Largest most, that's a funny way to describe things. Minus, so recognize this length is simply equal to this length minus this length, right? So this minus this. Okay. PS plus gamma H1. Now if we solve for this, PS minus PS, we're left with gamma times H2 minus H1. Okay. Now, go ahead and write 0.6 here, meters. All right, so let's calculate our volumes. Okay, so we'll start with 1. So how would you calculate the volume of a triangular prism such as this? Well, it's the cross section, a half times base times height times the depth. We'll call it W for width. Okay. So what's the base? The base we determined to be gamma H2 minus H1. So I'll write it like this, gamma H2 minus H1. The height is also H2 minus H1, isn't it? I'm just going to keep everything in variable form for now. Okay. So we see clearly that H2 minus H1 is 0.6, but I would like to keep things in variable form for now. So I'll write another H2 minus H1. So that's our height. And our width, we'll just leave that as W, okay? You could call it H2 minus H1 too, in this case, but we'll leave it like that for now, okay? Let's go ahead and figure out the specific weight of this fluid. Let's see. We are told that specific weight, specific gravity is 0.9. And we know that's equal to the ratio of the specific weight of the fluid to the specific weight of water. Okay. Oh, that's correct. Okay. We want the specific weight. So the specific weight is 0.9 times the specific weight of water, which I don't know off the top of my head for... Actually doing I think it's 60... Yeah, I'm going to be safe. Let me be clear. Specific weight is equal to 0.9 times the specific weight of water, which which is equal to 0.9 times the density of water times gravity, equals 0.9. I know the density of water in these units. Approximately 1,000 kilograms per cubic meter times 9.81 meters per second squared, right? Okay. So the specific weight is going to be 0.9 times, actually you can't see that whole calculator, so let me use my other calculator. Sorry y'all, didn't come to school prepared today. All right, specific weight of, and I shouldn't be calling this water because we're talking about oil. I may have said water, but I meant oil. The specific weight of oil is equal to 8829 newtons per cubic meter. Okay. Nice. Nice. Okay. So we have 1/2 times 8829 newtons per cubic meter. And I'm just going to go ahead and write all of these terms as one term cubed, since they're all the same, right? H2 minus H1 is 0.6. We got 2 of those here, and then we got a square cross section, so that makes 3. So 0.6 meters, we got that cubed. Calculate this. We have an answer of 953.5 newtons. Now you see exactly why I say so-called volume, because this is a volume expression, but there are Newton units, okay? Newton is not equal to cubic meters, okay? That's pretty clear. I trust you all get that. So now we know component 1 of our pressure prism volume, okay? What about component 2? Well, heck, that's even easier, okay? It's the base times the height times the width. Base, height, width. The base is PS plus gamma H1. The height is H2 minus H1. And the width is, we'll call it H2 minus H1, but we know it's 0.6. So this is equal to 50,000 pascals plus the specific weight, 8829 newton per cubic meter. Okay. Times 0.6 meters squared. And I forgot to multiply this specific weight by 0.6 meters, okay? And this square is coming from just simply multiplying these two together. Now, if I plug that into my calculator, oh, Oh, gamma H1. Gamma H1. Made a mistake here, y'all. Check it out. Check it out. These problems can be tricky if you're not careful, okay? H1. H1 is 2 meters, okay? So this is 2 meters. And if I correct that, we get 24.356 kilonewtons. Okay. So now we know the volume of our pressure prism is equal to our resultant force equals 953.5 plus, well, forgot my units. That's newtons plus 24.356 kilonewtons. And that's going to be equal to 25.31 kilonewtons. All right, that is our resultant force. Let me box that in to show my final answer for this part of the question. Okay, we also want to know the vertical location at which this force occurs. So let's take a look at the free body diagram of this, okay? Free body diagram of the surface. Here's our surface, okay? We have a resultant force acting on our surface. We also have 2 component forces acting on it that add up to make that. So we can include those. So F1 is the triangular one. Go ahead and label this FR. And we've got something here, F1, and one here, F2. Okay, these magnitudes are not drawn to scale. FR would be the largest. Now, if we look at a point, call it point O, and we sum the moments about point O, we know that this thing isn't rotating, right? Now, I should note that, let me be very clear here, these are not acting consecutively, okay? It's not FR is acting on top of F1 and F2. I've simply drawn them here to show the equivalence. So if we look at, so if we write out the sum of the moments, we get, well, actually, let me label my distances real quick. Okay. Let's go, let's see, this is the bottom. Make that a little bit nicer. That's the bottom. We've got some distance to here, some distance to here, some distance to here. Right, something about O. We'll call this Y1, Y2, and YR, okay? Now, what are those? Well, the force from 1 and 2 go through the centroid of the shapes 1 and 2, respectively. So, the centroid in the vertical direction here, since we're talking about the vertical direction of this shape, the y component of the centroid is 1/3 of this height. And for a square, the y component of the centroid is 1/2 of this length, right? So we know this length is 0.6, so half of that is 0.3. 1/3 of this is 0.2, okay? So I'll write that here. y1 equals 0.2. y2 equals 0.3. Okay. Sum of the moments. Let me make that a little bit bigger. Sum of the moments equals FR YR. And that also equals F1 Y1 plus F2 Y2. Okay? So now we have a nice equation that we can solve for YR. That's the only unknown in this case. We solved for force due to the triangle, force due to the square, and the centroidal locations of those respective forces. So YR is equal to F1 Y1 plus F2 Y2 divided by FR. Okay, F1 was, I called it V1 here. We could say F1. Okay. F1 was 953.5. 953.5 newtons times 0.2 meters. These are meters. Plus 24.356 kilonewtons times 0.3 meters all over 25.31 kilonewtons. And we're going to get let's see, 0.9535 kilonewtons times 0.2 plus 24.356 times 0.3 divided by 25.31. And we get that our resultant height, by the way, this is from the bottom, right? This is from the bottom. That's 0.296 meters from the bottom, okay? And the question asks for the vertical location at which it appears, so it doesn't specify a reference location. So reference from the bottom, that resultant force is 0.296 meters from the bottom, okay? So that is going to be it for this problem. Thank you all for watching. Please comment down below with any recommendations you have for other topics or problems that you'd be interested in me solving. Please also like, share, and subscribe to the channel if you found it helpful. And I hope you have a wonderful day.